1 minus x squared. And we're supposed to find the Maclaurin series using the definition. Oh. Well, there's a much easier way to do this. So we know that if we have 1 over 1 minus x, that's this. That's this Maclaurin series. And if you take the derivative of this, this is going to be 1 over 1 minus x squared when you take the derivative. And over here, you're going to get n x to the n minus 1. But the problem is that this goes from 0 to infinity now. And so to get 9, it would be 9 over 1 minus x squared. When n is 0, this is gone. So it's really going from 1 to infinity. So really, it's going from 1, okay? Because no term when n equals 0, because that's zeroed out. It's just we're taking the derivative and the constant term's gone. So you get this right here, 9n x to the n minus 1. Okay, now this is kind of tricky because their answer is you want to go from 0 to infinity, okay? So the answer they want is going from 0 to infinity. So, I mean, this right here is an answer, but they might mark it wrong if you put that in, or maybe they'll mark it right. Who knows? Did you get this by chance?
No. So we were looking at it and we were doing a different one than that Maclaurin series. I can try to put it in and see if I get that.
You have a different number up here. Is that it?
No, it's the same number, but we were just approaching it wrong.
Okay. So, I mean, the problem says use the definition of Maclaurin series. So I'm not sure if I'm actually doing it right or not. But you might have to do the following. So whether these are n's or whether it's some other variable, it doesn't really matter. Let me just change them to k's. That doesn't really matter. It's just a variable. I mean, and it's still 9 over 1 minus x squared. As long as you don't change this x to something else, the x stays the same. And then, so what you can do is to make this go from 0, you go like this. You go k equals 1. If you force there to be a 0 on the right-hand side, then this is k plus 1. So then you're going to let n equal k plus 1. And this will be, so this is, so that means k is n minus 1. Also, so if you change this k to an n minus 1, and you change this k to an n minus 1, and you change that k, and you change this k to an n minus 1, then you end up with, wait a minute, what's this, k? Okay, I can't get my basic math right. I've screwed up on the basic arithmetic. Look, I don't know, maybe this is COVID vaccine that affected me. Okay, so if k equals 1, then it's k minus 1 equals 0. So k is n plus 1. So plus 1, plus 1, plus 1. And Here you get n equals 0 to infinity, 9 times n plus 1, x to the n. And that should work right there, And this might also work, I'm not sure. This for sure works. And the radius of convergence is 1 because this radius of convergence is 1. Okay, so does that make sense?
Yeah, it does.
Okay, and what other questions are there?
That's it. Will this come up often where you have to change the n equals 0 to n equals 1 and then do how we did it with the k? Would that come up often?
No, I'll avoid letting that come up on you guys.
Oh, okay. Thanks.
I didn't realize that it would come up in this problem. And if you do it, if you write it like this, then I would, on the exam, I would probably overwrite it. Because even if you go from 0 to infinity, that's fine. And put that in, then you should be correct. Yeah. Okay. So, yeah, let's get into more exercises. Let's get into 11 section 11.11. And the homework here is really short. So the nth Taylor polynomial is introducing that concept. So the nth Taylor polynomial. And what that means is you've got these i's right here. It could be k's or whatever, or j's, but they chose to put i's, so I'm just going to go along with it. The nth Taylor polynomial, and that's the key, it's the nth one, is this. Okay, so for example, if your function is, let's say, the binomial function, okay, and that just goes like this. That goes from 0 to infinity x to the n. Then let's say the third Taylor polynomial, what happens there is you just keep on writing terms out, until you get to the x cubed term. So it'd be just that, and that's where you ended off. If it's the fourth polynomial, then you go plus x to the fourth. Okay, so you're just writing out all the terms up to that certain point. And the remainder, this represents all the rest of the terms. Or that would be going from I equals n plus 1 to infinity of the terms. Okay, so the whole series will go from 0 to infinity. And Taylor polynomial goes from 0 to n. The remainder is called the remainder. After the Taylor polynomial will be the rest of them, the rest of the terms, n plus 1 to infinity. So this plus that is going to give you your function. Okay, and so and this is also called the error. Okay, it's the error, or the magnitude of the error, because it's absolute values. And here's an estimate right here. This is called Taylor's estimate. So when it says use Taylor's estimate, that's what it's referring to. Let me pull up the homework exercise here for a second. That will come up later. Oh yeah, I'm sorry. It's called Taylor's inequality. Oh, darn it. Okay, so this inequality here is called Taylor's inequality. So basically, if you have the nth Taylor polynomial, t sub n of x, which is this, then you have this error. When you're estimating with this polynomial, you have this error here. And it's given by this right here. And an estimate of that error is all you need is the next derivative. And if you have the next derivative being less than or equal to m, then the remainder is less than or equal to m over n plus 1 factorial. And x minus a to the n plus 1. Other things you could use would be if your Taylor series is alternating, you can use alternating series estimation, which is just the next term in the series. Or you can use a graph to also figure out the estimate the magnitude of the error. And I'll make one quick note right here. And this is a sort of a concept that you might be familiar with. So T1 of x is the linear approximation. And so T2 of x would be you're approximating with a quadratic. You're approximating your function with a quadratic. And T3 would be you're approximating with a cubic. As you increase, get more and more, then your approximation tends to be better. Okay, so, and a linear approximation, by that I mean that is the tangent line. Maybe I should have said that. Okay, so T1 of x is the tangent line at x equals a, or a f of a. Okay, it's the tangent line to the curve at x equals a. So you're getting better and better approximation. So, you know, the tangent line is a linear approximation, but these are the Taylor polynomials as you get are going to be better and better approximations. When you're close to A, when you're further away from A, then it's not so great. Okay, so let's do some finding of Taylor polynomials. First one is the natural log of x centered at a equals 0. And we want the T3. So that means we need to go up to the x cubed term. So once again, we choose n, and then the nth derivative at x, the nth derivative at a, which is 1. This is 1, so you gotta make sure that's a. And then the nth derivative at a, which is 1 divided by n factorial. And then over here, I'm gonna put the term, the corresponding term. Okay, so we only have to go down to 3, and that will, because that will give us the Taylor polynomial. So you just have to do 0, 1, 2, 3. Okay, so the original function is log of x. You plug a 1 in, you get 0. So that's just gone. So there's no term there. Okay, when x is 1, that's the first derivative, so that's 1 over x. When you put a 1 in, you get 1. And so then you're dividing by 1 factorial, you get 1. And so the term will be x minus a, which is a is 1, so that'll be x minus 1. Okay, so make sure that you put x minus a. Sometimes you can get into the habit, if you do this a lot of these, most of the time it's gonna be the Maclaurin series where a is 0, so you're just gonna put x. Okay, but you know, put x minus a. Okay, the derivative of this would be negative 1 over x squared. And if you put a 1 in here, you get negative 1. And over 2 factorial, that's going to be negative 1/2. And so this is negative 1/2 x minus 1 squared, because this n is 2. And then the next one is when n is 3, the next derivative is positive 2 over x cubed. Well, that's going to be 3. And when you put a 1 in for x, you get 2. And so 2 divided by 3 factorial is 1/3. So the next term is 1/3, x minus 1 to the 3rd power. So T3 of x will be, just add these terms up. So x minus 1. You can put parentheses or not put parentheses, either way. Minus this term right here, x minus 1 squared over 2, plus x minus 1 cubed over 3. So that will be the T3 polynomial. Okay, part 2. We're supposed to graph these on the same screen. So, of course, let's go and use GeoGebra. So the original function is log x. So you're going to graph y equals log x, and then you're going to graph y equals this, in two different terms. So let's do that. So y equals log x and y equals this. That's what we're going to use on GeoGebra. So come over here to GeoGebra, start up the calculator, and log x was the first one. There it is right there. And it's 1 is where we're centered about. So let's maybe we can zero in on that a little bit. Okay, and now we put in the function x minus 1 minus, and notice that right now, as we put the first term in, this is the tangent line. And this if we just had the first term, that would be T1, which is the tangent line to the curve at that point. You put the next term in. That's over 2. That is approximating this logarithm, this green one, with a parabola right here. That's the parabola that best fits it if you're going, as you go to that point. And then the third one, put the third value in there. And that's the function. So zero in that a little bit. So the blue one is the T3, and the green one is the original function. So let's go back to GeoGebra. And it looks like it was this first one right here. This graph here. So this red one is y equals T3 of x. And the blue one is y equals log x. Okay, great. Any questions or comments on that?
No.
Let's go on to number 2 then. Find the Taylor polynomial centered at 0. Okay, this is great because we know that f of x, we know that e to the x is the summation of x to the n over n factorial. That's for e to the x. If this was e to the x, it would be x to the n over n factorial. But it's negative 2x, e to the negative 2x. So just put negative 2x in there, and there we go. That's going to be it right there. And this x can go in. Let's see here. Let me think about this for a minute. That's negative 2 to the n, x to the n over n factorial. Then we can put the x in. So the T3 of x, which is what we're looking for, T3, will be, you're just going to sum up to where this power is going to be 3. So that's actually only going to 2, because when n is 2, this is to the third power. Okay, so when n is 0, we get negative 2 to the 0, which is 1, sorry. And then this is gone, and it's just 1. So it's 1. And when n is 1, we get minus 2. And this would be, oh, wait a minute, x. Hold on, this is x. I'm sorry. Because when n is 0, this is x to the 1, so that's x. Sorry about that. And then when n is 1, okay, then we're dividing by 1 factorial here. Right there. And then when n is 2, we get negative 2 to the 2, which is 4 x cubed over 2 factorial. Okay, so that's going to be x minus 2x squared plus 2x cubed. Okay, that's our T3 of x right there. So let's go ahead and go over, graph those again and using GeoGebra. And again, we're going to graph what x equals, or fx equals x e to the negative 2x, and also the polynomial that we just came up with. So I'm going to change that. So x e to the negative 2x, that's the first one. And then the second one, we just change this to whatever, to what the T3 polynomial was. X minus 2x. Wait a minute, something's wrong. Oh no, this is great. And so here, this is what we're looking at right here. So this blue one is the T3 polynomial. The green one is the function. Here's our function. So the blue one is an approximation of the function. It's pretty good. It looks like a pretty good approximation up until about here, and then down up until about there. Looks like they're pretty close. Now, of course, as you get away from 0, these are different by quite a bit. Okay, they differ by quite a bit. So this is only a good approximation when you're close to x equals 0. Okay, so let's see here. Let's see, which one is it? It's going to be the first one again. Okay, so this is, this black one is y equals T3 of x, and the blue one is y equals x e to the negative 2x. Okay, so that would be this one. I mean, some of these you can tell that there's no way this can be true because it has to be parallel right at the tangent right at the point. This one right here is just it looks like, yeah, this one is just the linear approximation, the T1. This is T1. And then this might be wait a minute. Maybe T2, but I'm thinking, oh yeah, the black one might be T2. Maybe not though. Yeah, I think the black one's T2, and the blue one is still this right here. Okay, so let's go ahead and, any questions about that before we move on?
No, all good.
Okay, let's go to number 3 then. So f of x equals x to the 2/3, a equals 1, n equals 3. Approximate with the Taylor polynomial of degree 3. So again, we're looking for T3 for this function when a is 1. So I make our little list right here, n. We just need to go to 3 again. So the nth derivative, and it's originally x to the 2/3. And the nth derivative evaluated at 1, and then the nth derivative evaluated at 1 divided by n factorial and the term. Okay, so you put a 1 in here, you get 1, and then that's 1. So the term is going to be x minus 1 again. No, wait, no, I'm wrong. N is 0. I'm sorry. N is 0. So it's 1 times x minus 1 to the 0th power, which is just 1. So when n is 0, you're just going to get the so when n is 0, you just get the constant. Okay, now when n is 1, take the first derivative, that's 2/3. X to the subtract 1 from this, you get negative 1/3. You plug a 1 in, you just get 2/3. Divide by 1 factorial, still 2/3. So that's 2/3 x minus 1. Right, so 1 is x minus 1 to the first power. Okay. Another derivative, this negative 1/3 comes down, so you got negative 2/9. Subtract 1 from that, you get negative 4/3. If you put a 1 in, you get negative 2/9. Now you're going to divide by 2. Oops. That's all divided by 2 factorial. So that's going to be negative 1/9. So negative 1/9 x minus 1 squared, because that's n is 2. Okay, then one more derivative. Negative 4/3 comes down. You get a positive 8/27. X to the negative 7/3. Put a 1 in here, you get 8/27. Now you're going to divide by 3 factorials. That's 3 and 2, which is going to give you 4/81. Okay, 27 times 3 is 81. 8 divided by 2 is 4. So 4/81. So that's 4/81 x minus 1 cubed. Okay, so that means T3 is going to be 1 plus 2/3 x minus 1. I'm just copying these terms down. Minus 1/9 x minus 1 squared plus 4/81 x minus 1 cubed. Okay, so it says use Taylor's inequality to estimate the accuracy of the approximation when x lies in this interval here from from 0.8 to 1.8. No, from 0.8 to 1.2. Okay, the Taylor's inequality depends on the next term in this. So we just calculate this term right here. So take another derivative. So I got a negative 7/3 coming down. Wow. So that's negative 56 over 27 times 3, that's 81. So negative 56 over 81 x to the negative 10/3. Okay, now let me go back and show you why. Let me just give you an idea of what we're doing and the steps that we're doing. So this is the n plus first term. Let me show you why we did that. Okay, so here's Taylor's inequality right here. First thing we want to do is find an upper bound for the n plus first derivative at x. Okay, and we have the n plus first derivative. That's this right here. And that's negative 56 over 81. Well, let's put absolute values, okay? Now, this is x to the negative 10/3. That's the same as 1 over x to the positive 10/3. Okay, now, on this interval, the interval from 0.8, okay, so here's the interval right here. On this interval, if you you say you're dividing by x to the 10/3. That is going to be, this whole quantity is going to be largest when you put the 0.8 in. Okay, because when you put a 1.2 in, you're dividing by a larger number. So you're going to get a smaller number. So the largest that you can get is by plugging in the 0.8 to the 10/3. This will be the largest. Okay, so that's going to be your m. Okay, or right here, this m right here. The m plus first derivative x. That in that interval, the largest it can be is when x is 0.8 because you're dividing by a smaller number. So that's the quantity that we have. Now, the remainder term is less than or equal to m over m plus 1 factorial times this right here, x minus a to the m plus first power. Okay. So that we go to the next stage, and that is r sub n of x is less than or equal to m over n plus 1 factorial times x minus a to the m plus first power. Now, that m is this right here. N plus 1 is 4, okay? So that's 4 factorial there. Okay, so this right here gets made to a 4 factorial. And in this interval, let me illustrate this a little bit. Okay, so in the interval, you have 1 in the middle. You've got 0.8 there. That's a bad 0.8. And you have 1.2 there. The distance, so A is 1, okay? So the distance from there to there is 0.2. This distance right here is also 0.2. Okay, so the most this can be is 0.2. And then again, this is a 4 to the 4th power. So you calculate this with the calculator. And I got approximately, let me see here. .000009697. You're supposed to go 8 decimal places, is why. Okay, so when you're that close, that's what your error is going to be. Okay, and then, so that's part B. That's part B, which is just this, just evaluating that right there. It's kind of messy, but yeah, calculator can handle it. Okay, for part C, you want to graph Rn of x. Okay, so the graph, let me see here. Absolute value Rn x. Now Rn of x is going to be your T3 of x minus your function. Okay, that's what that's going to be. So we just put that, so it's all this minus x to the 2/3. So all that minus x to the 2/3. So anyway, I'm gonna write that out. Actually, it's the other way around. It's the function minus the Taylor polynomial. That's what your error is. Okay, your error is actually the other way around. Okay, but it's going to be easier if we just put the Taylor polynomial and then subtract that rather than have to put change sign changes on all of these. So, or I figured that would be. Okay, so let's go ahead and graph it using GeoGebra. So here I'm just going to delete the second graph here, and it can handle absolute values, fortunately. So absolute value, and we have 1 plus 2/3 x minus 1 minus 1/9 x minus 1 squared. It's the T3 polynomial. Minus x to the 2/3. Okay, looks kind of weird. But we're only interested in the interval from 0.8 to 1.2. So we're only interested in going from 0.8 to 1.2. So you can zero in on that. 0.8 to 1.2. It looks like that basically. I don't know how to change the Y scale to give it to view it better, but it comes down and then goes up like that. So there's this first one. Okay, any questions on that?
No.
Great. One more exercise, and whoa, we only have 6 minutes left, so we got a quiz. So again, a is 1. Here we have log of 1 plus x. One plus 2x. I'm sorry. We can exploit the log of 1 plus x formula. Yeah, let's just do that. Okay, so log. No, wait, no, that's about 1. So oops, that doesn't. No, we can't exploit that. Because a is 1. So darn it. Okay, that's okay. So n, and then nth derivative. Nth derivative evaluated at 1. Evaluated at 1 divided by n factorial and the term. Okay. 0, 1, 2. Again, it's the third degree Taylor polynomial. Okay, so the original function is log of 1 plus 2x. Now, if you put a 1 in there, you get log of 3. So this will be log 3, and the term will be log 3 times 1. That's going to be the first term of the T3. Okay, the first derivative is going to be, it's 1 over 1 plus 2x times the derivative of 2x, which is 2. If you put a 1 in here, you get 2 over 3. And of course, that's 2 over 3 because you're dividing by just 1 factorial. So that's 2/3 x minus 1. Next derivative is, this can also be written as 2 times 1 plus 2x to the -1. So you take another derivative, you have -1 coming down, so that's negative. And then -2. And then they have a 2 coming out, so that's 4. Okay, you put a 1 in, you're going to get -4 over, okay, over, this is -2 means it's in the denominator, so that's 3 squared, which is 9. And then you're going to divide by 2, so that's negative 2 over 9. 1 squared. Okay, here, take another derivative. You've got the negative 2 coming down. That's raised to the negative 3. And another 2 comes out. So that's going to be 16, positive 16. And this is cubed, so it's 16 over 27. And dividing by 3 factorial is going to give you 8 over 81. Okay, so those are the terms for the Taylor polynomial. Log 3 plus 2/3 x minus 1 minus 2/9 x minus 1 squared plus 8 over 81 x minus 1 cubed. Okay, there's your T3. Okay, Taylor's inequality. That means we go to the fourth derivative. I ran out of the real estate here. Oh well. I'll just come down here. The fourth derivative. This negative 3 comes down, and also you have a 2 coming out. So, well, that's negative 96, and this is 1 plus 2x to the negative 4. When you put a 1 in here, you're going to get negative 96 over 3 to the 4th, which is 81. Whoa. No. Don't do the rest of that. Because what we want to do is we want to find m. Okay, so fn, n plus 1 of x, that's equal to this absolute value of this, which is 96 over 1 plus 2x to the 4th power. Okay, now you're looking for what's the largest that can be. And the largest that can be is when this gives you the largest. This makes this the largest when x is 0.5. Okay, so that's 96 over, because it makes the denominator the smallest. Okay, so that's going in right there. And that's a 6. Okay, so that's our m. So m is 6. And the m that I'm talking about is this m right here. This m right here in the Taylor's inequality. And then the r sub n, the magnitude of r sub n of x is also equal to m, which is a 6 there, over n plus 1 factorial times this. Okay, so I'll go ahead and do that. And again, this is 6. N plus 1 is 4, so that's 4 factorial. Oops. And this one right here is the distance between your center, which is 1, and either endpoint. So that's 0.5 to the 4th power. And in the calculator, that gives you 0.015625. 0.015625. Okay, and then for the third part, again, we're going to graph y equals the absolute value of that minus log of 1 plus 2x. Because they want to graph this right here. They want to graph that right here. And that's what that is. The absolute value. It's the Rn of x is this one divided by that one. I mean, or this one subtracting that one. But the absolute values, you can flip the other way to do the absolute value. Okay. So go back to our good friend GeoGebra. Where's GeoGebra? Oh, there it is. Okay, GeoGebra. Okay, now we zoom back out because, and we're gonna change this right here. So that's log of 3 plus 2/3 x minus 1 minus 2/9 plus 8/81. I might have done that. And then we're subtracting log of 1 plus 2x. Okay. Not right. Oh, I might have graphed the wrong thing on the last problem. It doesn't seem to have made that much of a difference. Oh well. Okay, so there's our T3 polynomial here minus f of x. And it looks like it's like this. It comes down and it goes back up like that. And here's 1 right there. Well, we're only interested in 0.5. 0.5 to 1.5 right here. From here, 0.5 to 1.5. So it comes down and goes back up. Comes down, hits 0, it goes back up. So that is going to be the second one. I guess that if the scale wasn't correct, maybe it could be the third one, but